Well, hey there, everyone. Let's begin the final exam review. Alright. Yeah, sadly, I don't actually play Dota 2. Ben and I definitely need to do some more streaming over the summer. You never got your exam 1 grade. So, yeah, if you guys are wondering where your exam 2 grades are, they are done, actually. I spent all of last week grading. It was actually kind of terrible. Not the grades on the exams themselves, but just the process of grading all of that stuff was really bad. But, and it took forever. I'll send all that out tonight, I think. I just have to kind of like get a good system to send your results back to you. I'm going to email you guys each with like a PDF of your exam that I've put some marks on. I might write up some solutions for it. So that's where I'm going with that. I could also, the one thing I might do is just post the numbers to Blackboard first, and then sometime tonight you'll get your actual exam back, probably. I'm just trying to write a script to do that so that I don't have to do it 80 times, because that could take me an hour or two to do that, and that would be terrible. Okay. Yeah, so the final exam is going to be like the thing that I'm about to show you. So let's begin, I guess. I think the final exam might be a little easier than what I'm about to show you. I put some interesting problems on it, but you know, I totally understand your sleep situation. I woke up somewhere around 11:30 after going to bed at about 5 or 6, maybe something like that a.m. So, okay, let's yeah, I mean, if you want, so one idea that I've had is that the final exam could be essentially like a multiple choice exam on Blackboard. So, I don't know what you guys are thinking about that. Anyway, I mean, the multiple choice exam on Blackboard would definitely get you guys grades back very quickly, right? We would have your grades done within yeah, I'm not sure exactly what we would do in terms of, I think you'd probably only have, well, maybe I'd give you a few days to do it. You inherently detest multiple choice. As it turns out, you'll be surprised to hear that I actually kind of hate it too. So, I mean, really, who cares if you guys torture me with grading, right? If I've tortured you with the exam, that's only fair turnaround that the grading caused me some degree of pain and misery. But anyway, that's just kind of the idea. I am thinking of, and I do promise you that the multiple choice would be very burn that idea with fire. Well, so you know, that's you like single choice. Yeah, so I mean, I don't know. Maybe if I come up with some examples, I'll give them. Like, obviously, this problem cannot be done with multiple choice, or maybe it can. So, for instance, let's just do this problem the standard way, and then let's see. How do I actually? I think there we go. So, how do we show? Let's just do this problem the standard way, and then I will invent a multiple choice question that tests the same concept, right? So that's the primary thing. So the idea here is I'm going to test your ability to use induction. So here's what we're going to do. We'll say, okay, does 3 divide n cubed plus 59n for n is equal to 0? And so the answer is, does 3 divide 0? Which it does, right? Because 0 divided by 3 is equal to 0, which is in the natural numbers. Is it? Sorry. Let me just, okay, I'm gonna hold my tablet down on my lap rather than on the desk. I think the problem is if I put the tablet near the mic, it kind of rubs back and forth like this. Okay. All right. So this is true. All right, so this is our base case. And so now let's do the inductive case. Which is to assume let's see, what do we assume? Well, so here it says for all n is bigger than or equal to 0, so it tells you what the base case is, right? It says, it tells you what base case to use. Yeah, I think it just rolled over some paper. Let me clean up my desk just a little bit. Let me throw these papers somewhere. All right, there we go. Oh, more papers. There we go. Okay. Yeah, so we're going to assume that 3 divides n cubed plus 59n. And then we want to consider n plus 1 cubed plus 59 n plus 1. Oh, don't worry. If you used 1 instead of 0, would I take off points? Probably not. I would just be a little confused, but I wouldn't care. So if you expand this, right, so we expand the algebra, and we get n cubed plus 3n squared plus 3n plus 1 plus 59n plus 1. Nope. 59. How big is this? Okay, let's shrink it down. Okay. All right. So what we're going to do here is we're going to group this term and this term. And when we group those terms, we're going to see that we get the inductive hypothesis. So we know that 3 divides n cubed plus 59n. And then we have the rest of the stuff. 3n squared, which has a nice 3 in front of it, so that means that 3 divides it, plus 3n, has another 3 in front of it. And then we have the rest of the stuff plus 1 plus 60, right? These two terms here. And, well, I'm sorry, not 1 plus 60, 1 plus 59. I jumped ahead for a second. 1 plus 59, and so then when all this adds together, we get 3n squared plus 3n plus 60. And so the good news is that you can pretty quickly see that this divides, or 3 divides this. And nothing's touching the desk now, so I'm a little confused. I hope I'm not doing something crazy. 3 divides this stuff. Okay, so given the fact that 3 divides all this stuff and that 3 divides this n cubed plus 59n, what we know is that 3 divides the whole thing, and therefore we are done, right? So this is the inductive hypothesis part here. This is the garbage term that we have to make sure that it divides. So there we go. All right. So any questions about this induction problem? All right. Yeah, that's right. So how could this be multiple choice? Well, let's think about it. So if I say something like, maybe I would just write out the proof. So I would say something like, select the correct argument. And so it would start here, probably be like, assume this, and then I'd write out some of this algebra. And then maybe I would say instead, like, the wrong answers could be assume that 3 divides n plus 1 cubed plus 59 n plus 1, and then I try to show that it divides, right? Show that it goes backwards or something, something like this. And if I did all the algebra to show that, this is not induction because it's going backwards, I could do one where, I don't know, something like that. I mean, it's hard to yeah, I'm thinking that's like, and then like maybe another one, another one that's relatively close. And then maybe D would be the garbage answer, right? Okay. So, I mean, that's just an idea. Let's do another thing. So we want to show, for instance, that 6 divides 11 to the n plus 1 minus 5 to the n, for all n in the naturals. So we start with our base case, which is 11. Interesting. Okay. Is this right? Let me just think. I made this problem up, so it could be that I need a plus here and not a minus, but let's just check. So if we stick in 0, so 0 plus 1 will give us 11, and then minus 5 to the, I think this actually should be a plus. I think this is let's call this a typo. Let's change this to plus. Plus 5 to the 0 power, and that works. So that works. Okay. So the actual answer is that 11 to the n plus 1 minus 5 to the n does not, 6 does not divide that, so that's false. But we have to fix that typo. Okay, so once I did that, what do? We do the inductive case, where we say, okay, assume that 6 divides 11 to the n plus 1, and then remember it's plus now, not minus, 5 to the n. And so then what we're going to do is we're going to say, well, look at, so we're going to consider 11 to the n plus 1, and I mean, you don't have to write this out in this kind of painful detail, but this is what induction does, right? It takes this n and it replaces it with n plus 1. So even if it is an n plus 1 here, that doesn't just leave it as n plus 1, right? This shifts it up to 11 to the n plus 2, right? Plus 5 to the n plus 1, like that. Okay. So now what do? So what we do now is we say, okay, 11 to the n plus 2 is equal to 11 times 11 to the n plus 1. And 5 to the n plus 1 is equal to 5 times 5 to the n. And so because of these two facts, we can rewrite this expression just a little bit. So we say, oh yeah, and then it's the trick that you guys love. And so remember what the trick is here. The trick is you take the bigger number, right? And you split it up. So, and then you just remember that 11 is equal to 5 plus 6. So if 11 is equal to 5 plus 6, what that means is that... yeah, I'm sorry, I don't know what's causing it. Okay. Anyway. Will you be given one that's false? No. That is absolutely not going to happen on the exam. Unless, of course, I totally screw up or something like that. So, no. I will only ask you to prove true things, especially if it says, show that. If I asked you to show that a false thing is true, then... yeah, that'd be pretty horrible. So... okay, so let's think about it this way. So we have 11 to the n plus 1, and this is equal to 5 plus 6, plus 5 times 5 to the n. And so this is equal to 11 to the n plus 1, and times that 5. So I'm going to factor the 5 out, and then I'm going to write 5 to the n here. And then we have the remainder term, plus 6 times 11 to the n, like this. And so the good news is that this term here is the inductive hypothesis. So we know that 6 divides this term, right? And also we know that 6 divides this term because there's this nice 6 sitting right here. So anyway, so that's that. There's actually a trick to doing these problems, and I'm going to show you the trick to, for instance, this problem without induction. So, because I think it's kind of interesting. It's something that I didn't really cover too much. So if I want to show that 3 divides n cubed plus 59n, yeah, I can go over the algebra and I'll just go over the algebra. So here, what we're doing is you have 11 to the n plus 2 plus 5 to the n plus 1. And what you do is you split that up as, I should say 5 plus 6 times 11 to the n plus 1 plus 5 to the, or I should say 5 times 5 to the n. And so the point here is that what we're going to do is we're going to regroup. Right, because we have this 5 here and we have this 5 here. So what we can do is we can pull these 5s out, and if we do that, then this 5 comes with an 11 to the n plus 1, and this 5 comes with a 5 to the n, like that. And then the remainder term is this 6 times 11 to the n plus 1. If you remember, I think there was that quiz in the earlier part of the semester, and when everybody would come up, what was I always saying? Was I saying that I would say something like 8 is equal to 3 plus 5 or something, right? And in this case, we don't have to, it's not 8 is equal to 3 plus 5. It's actually 11 is equal to 6 plus 5. Now, right? So that's the trick. Okay. So I'd like to go back to this problem for just a second and just talk about this for a moment. So there's another way to do this problem, which I think is kind of cool, and it doesn't involve induction. So if you take this equation here, n cubed plus 59n, and you mod it by 3, then n can either be 0, 1, or 2. And the reason is because if you take n and you mod it by 3, then there's only 3 possible. I mean, technically it could be like -2 mod 3, but then that's also the same thing as 1 mod 3. which is also the same thing as, I don't know, 4 mod 3, or 7 mod 3, or 10 mod 3, or whatever. So given that there's only 3 options, we can actually just test each one. So for instance, if you say, all right, if I plug in 0 here, 0 cubed plus 59 times 0, and then we take this thing mod 3, well, 0 mod 3 is actually 0, so that's good. What about 1? So we do 1 cubed plus 59 times 1, mod 3, and that's equal to 1 plus 59, which is 60. Well, 60 mod 3 is 0. This solution only applies to this kind of problem. Yeah, you can, well, I'll show you the other one in a second. And then so 2 cubed plus 59 times 2 is what? So this is equal to, or I guess congruent if we're going to use the technical notation. It's 8 plus 118. Yeah, I mean, induction works in a lot of different types of problems. This type of thing is a trick to do this specific problem, and a bunch of other problems that are like it. So what is 8 plus 118, if I can even think of it? I think it's 126. How many tricks do I have memorized? I don't know. But then the one thing to remember is that 126 is equal to 120 plus 6. And so 6 is divisible by 3, and 120 is divisible by 3. So 126 is divisible by 3. So it's concurrent to 0. So what this shows is that if n is anything congruent to 0 mod 3, so if it's 0, 3, 6, 9, 12, anything that's basically this is n is equal to 3k, then this statement is true. If it's 3k plus 1, then this statement is true. And if it's 3k plus 2, then this last statement is true. And in all cases, they're equivalent to 0 mod 3. When you're equivalent to 0 mod 3, that means you're divisible. So, yep. So that's a nice little fun trick. Okay. Let's look at another problem. So I put this one on the practice test. I think it might have, this is probably way too hard. So the problem on the actual test will be a very scaled back version of this thing. So we want to prove by induction that for any positive integer, this horrible thing is true. So 1 over 1 minus z to the n equals the sum from k equals 0 of n plus k minus 1 choose k times z to the k. Okay. So, and then basically this is the hint. And the nice thing about this hint, oh sure. So the nice thing about this hint is that, as it turns out, 1 over 1 minus z to the n is equal to the sum. Well, really, I'm not even going to write it like this. I'm going to write it in a stupider way, but actually it's going to be more illustrative of what I want. So what this summation here is really 1 plus z squared plus z cubed. Z is a variable, I guess. You can just call this all like a function of z plus, like, say, z to the 4th plus ... all the way up to infinity. So, and then we take this thing to the nth power. Yeah, n and k are constant. Well, k is the variable in the summation here, and n is, assume that n is fixed, at least for this case. So You know what? Maybe we should skip this problem. I don't know. I just wanted to pick an induction problem that didn't have to do with divisibility, but I think this thing might be insane. The way to but let me just finish the problem and then skip the rest of it. So the way to really think about this problem is that it's actually just the binomial theorem. Yeah. So, basically, you just need to... what's the way to think about it? Actually, you know what? I shouldn't even do that. This is stars and bars here. So the way you might do it if you're a mathematician, instead of using induction, is you could say, like, m plus k minus 1, choose k, is the number of ways to pick, or I guess to... Oh, I know, it's the number of ways to solve this equation. Yeah, this is good. It's the number of ways to solve the equation... What? x1 plus x, or let's just call it power 1 plus power 2 plus ... plus power n is equal to k. So as it turns out, this is equal to n plus k minus 1, choose n minus 1. So that's where the minus 1 is. Because if you see here, there are n variables. And so what do we know? What we know is if this is the number of ways to solve this equation, then we have to select one of the powers from each of the terms. And there's n terms. So what we're going to do is we'll say that we're going to select, from the first term, we'll select z to the power 1. And from the second term, we'll select z to the power 2 times z to the power 3, all the way to z to the power n. We know that all of those sum to k, so this is not times, this is, or not plus, this is times z to the power k. And then how many different solutions are there to that equation? There are n plus k minus 1, choose k of them. And so that's where that coefficient comes from. So as I say, maybe this problem is... I just picked it because it looked interesting, but I think actually it's a little horrible. You know, doing it by induction actually might be doable by you guys, but I think it would take you guys a while to like figure out which things are moving and which things are constant. Like for instance, in each one of these equations, n is constant, z is some fixed... You have to pretend like z is some fixed number, n is fixed, k is actually the thing that's moving because of this summation. But anyway, this is just another example of an induction problem that you could solve. Okay. Let's do this fun problem. So this is way easier. It's definitely a power series. Yeah, so the only trick to this problem is that I gave you guys P of A union B rather than P of A intersection B. Like this. So well, I guess I'm just writing down the double union formula for no reason, other than the fact that you actually kind of need it. So you say 0.6 is equal to 0.4 plus 0.32 minus x. Yeah, it's 0.6. Let me just erase that y so that it's... Yep, you do solve for the intersection. In this case, I'm just calling it x. So this is going to be 0.72 is equal to 0.6 minus x. So x is going to be equal to decimal 12. Yeah, so think about this. I think this is the first time in this class where I've invented a problem and the intersection is smaller than both of the original sets and actually makes sense. So this is success for me. Okay. I know. It's like, what is the probability that I screw up? Apparently it's like the probability of screwing up is something like 0.87. Yeah, remember, this is A given B and this is B given A. This is just conditional probability. Don't think about divisibility anymore. I don't even know what it means to divide numbers. So the probability of A given B, using the definition of conditional probability, is the probability of A intersection B. And remember, you just divide by the second thing. It's always divide by the second thing, so probability of B, which is, so in this case we'll have 0.12 divided by 0.32, which is a number, right? 12 divided by 32 is 6 divided by 16, which is 3/8, which is 0.375. That's a number we can actually compute. On the other hand, the probability of B given A is basically the same thing, except now A goes into the denominator. And so 0.12 divided by 0.4 is what? It's 12 divided by 40 is 3 divided by 10. Come on. Don't give up on me. You were working so well just a second ago. Yeah, my dog was trying to get my attention. She's staring at me right now. I stare right back. That's when the attack comes, not from the front, but from the sides. Does my dog like math? I don't think she's a world-class mathematician or anything. Come here. All right, let's just do one of these balls and urns problems. So she wishes she was a journalism student. Okay, so first we want to draw a tree representing the... oh, yeah. Okay, let's draw a tree representing the situation. So the way I invented this problem was that there's a 35% chance that we pick from the first urn. So this will be urn 1, urn 2, urn 3. There's a 0.35 chance that we get from this one. There's a 0.15 chance that we pick from this one. And there's a 0.5 chance that we pick from this one. Well, yeah, don't worry. If nothing else, there will definitely be an urn problem on the final. So here in the first one, there's 3 reds and 12 whites, so we'll have 3 out of 15 here, 12 out of 15 here. In the second urn, there's 17 and 4, so I made it stupid. So it'll be 17 out of 21, which is an unpleasant number to deal with because it has kind of, long decimals. And 4 out of 21. And in the third urn, it's 50-50, right? 1/2, 1/2. You could also write it as 10 out of 20, but you can also simplify, right? These are just, the reason why I'm writing these as fractions, I mean, I guess you can reduce these. You can't reduce these. So, okay. So when I say to draw a tree representing the situation, that's what I want. Yeah, 17 is my favorite. So what is the probability of picking a red ball? So the answer is either you go down this path, you get the 0.35, and you get the 3 out of 15, which I'm, again, not going to reduce because I've written it the same way there, plus 0.15 times 17 out of 21, plus 0.5 times 1/2. So if we want to evaluate this, we'd actually just, I guess, need a calculator or something. So let's do 0.35 times, I guess 3 out of 15 is just, what? 1/5, so that's just 0.2, plus 0.15 times the unfortunate 17 out of 21. Plus 0.5 times 1/2, which is known as 1/4, so 0.25. Overall, I get 0.441, which seems right. It's nice if you compute the answer. I mean, you guys have calculators and computers and all kinds of things. Oops. So, okay, what's the probability that we pick earn 1 and a white ball? So what's the probability that we pick U1 intersection W if it's multiple choice, the answers will be simplified. So if it's multiple choice, I mean, I can write down a bunch of different formulas and final answers, but I don't think I would ever actually make the formula not equal to the final answer. I would just kind of evaluate it for you guys. So if you have an intersection like this, it's actually going to be equal to the probability of earn 1 times the probability of white given earn 1. And so the good news is that this means that what we have is 0.35 is the probability of earn 1, so 0.35. And the probability of white given earn 1 is just written right here. Right? So this number here is the probability of getting a white thing given that we've picked earn 1 already. X and Y is X intersection Y. Oh, did I say, yeah, those are both true. Okay, and so here we get 4 out of 5, so 0.8. So actually we can evaluate that pretty easily. So 0.35 times 0.8. Oh, I should have been able to do that in my head. 0.28. All right. So now let's do, it is. Yes. So what is the probability that given we picked a white ball that we picked earn 2? So I've designed this problem so that if you write it out correctly, given that we picked a white ball, so given W, what is the probability of earn 2? So now you see that these numbers, you see this symbol and this symbol are flipped, right? So D is going to be Bayes' theorem. And so let's try to do Bayes' theorem on it. Let's get a new page. So how do we do Bayes' theorem? So remember that actually it's really just the probability of earn2 given white is really, you can just use conditional probability. It's the probability of earn2 times the probability of white given earn2 divided by, and the probability of a white thing. Now the thing about the probability of a white thing is that actually if you look at the tree, so we computed the probability of red here. So actually, if you know the probability of a red thing and there's only two possibilities, you can either get red or white, then what is the probability of white? Right? It's going to be 1 minus the probability of red. So it's going to be 1 minus 0.441, which is approximately 0.559. These are all approximations to like the thousandth decimal place, but you know, who cares? It is what I did. Yes. So, okay. So then the probability of earn2, I think, was 0.15. And the probability of white given earn2 is whatever it was. What was it? White given earn2. Was that the 4 out of 17? Let me check again. I think that's 4 out of 17. Yeah. 4 out of 21. And then what we're going to divide by is 0.35 times, I think it was, what, 0.8 plus 0.15 times 4 out of 21 plus 0.5 times 1/2. But the good news is if you actually did this calculation, you should come up with something close to 0.559. Let's actually do it. 0.35 times 0.8 plus 0.15 times 4 out of 21 plus 0.25. I get 0.5585714 blah, 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 blah. Yeah, so right, so here we have the probability of earn1 times the probability of white given earn1 plus the probability of earn2 times the probability of white given earn2 plus the probability of earn3 times the probability of white given earn3. So, okay. Oops, divide by 0.5, divide by 20. Is that really true? I have a hard time believing that. So what is 0.15 times 4 divided by 12? Okay, divided by 0.55857, whatever. Okay, so overall, when you actually compute this number, it's approximately equal to 0.0511. And the O is not a... it's about 5%. So what does this mean? Right, so we've computed this horrible thing. So what it means is that if you pick a white ball first, then the probability that it came out of earn2 is about 5%. So that's what it means, is that someone hands you the white ball and you say, okay, which urn did you pick it from? So you probably would not bet that they picked it from earn2 because there's only a 5% chance of that happening. All right. Questions about this? Cool. I guess I can always go back. So, well, so the trick to Bayes' theorem is that Bayes' theorem is just the definition of conditional probability. Kind of expanded. Because this is the definition of conditional probability here, right? This is just conditional probability. And technically, if you rewrote probability of white, if you replace that with all of this here, then you call that Bayes' theorem. What's the probability your hand gets stuck in turn one? Wait, not B. Probability of white. So the thing is that Bayes' theorem is just kind of a... It's a theorem that basically allows you to jump through this step and just kind of expand this term. And I mean, the only thing about Bayes' theorem is that it's a little bit confusing when you first see it. But what you realize is that what they're actually asking is for the probability of all the different ways to get to white. And that's what this denominator is. So it's a whole bunch of... remember that it was a summation in the denominator where it's like a sum. It's like the probability of what? AI times the probability of, say, B given AI, and divided by the sum of the probability of AK, probability of B given AK over K. So K is the index of the sum, and this is equal to the probability of, what was it again? Like maybe AI given B. So yeah, so you could also just, yeah, because we already knew what the probability of red was, so you could have just done one. It's not P of R minus 1, but it's 1 minus P of R. But basically, yeah. If you do P of R minus 1, you'll just get the negative of the right answer, so that's okay. You'll realize that pretty quickly. Okay. So apparently haplogroup H exists in Europe, and so I guesstimated that haplogroup H exists in about 5.7% of the population. The good news is you don't need to know anything about haplogroup H other than 5.7%. Yeah, I mean, I guess a negative probability is that it can't happen in this universe, but there's another universe where it's very unlikely for it to happen. So assume that the genetic test has... So I'm using the terms sensitivity and specificity here, which are kind of horrible terms. I really hate them, which is why I describe what they mean. So the genetic test has a 99% sensitivity, which means that if someone is in haplogroup H, say that there's a 99% chance to detect it, so 99% of the time it comes out positive. So here if we have 0.57 to be in haplogroup H, and this is not H, oh, I'm sorry, 057. And so this will be 0.943, right? And so this will be not H. You can also use H complement or, not H, or whatever you want to say. If you're in this group, then there's a 0.99 chance that you're going to test positive for being in haplogroup H. Yeah, you can also do that. And then there's like negative. P and N. So, and then here the probability is 0.01, and so here if you don't have it, then there's a 95% chance. Then you're going to test negative. There's a 5% chance that you're going to test positive. So this is part A. Part A is drawing a tree of the situation. There we go. So then what's the probability of testing positive? The probability I'll use PR for probability so that I can use P for this. I'll use POS for positive rather than it's a slight difficulty. I don't want to use what I really am trying to avoid here is just writing the probability of the set P. Right? This is no good. So, all right, the probability of testing positive, as you know, should be something like 0.057. Yeah, it stands for position, or positive. I have no idea what other thing it could possibly stand for. So let's calculate this number. Oh, positron. Yeah, but if you wanted to do a positron, you should just write E plus. .057 times 0.99 plus 0.943 times 0.05. And the number I get is 0.10358. So in a way, we actually know. So what is the probability? What is the probability that, given you have tested as being a member of Group H, you are actually in Group H? So this means that you have tested, meaning that you are positive. What's the probability you're actually in Group H? And so this is asking, get the probability that you're in Group H, given that you've tested positive for being in Group H. And so you actually, it is technically Bayes' theorem, but we've already computed the denominator. So we can short circuit Bayes' theorem and just do 0.057 times 0.99 divided by 0.10358, which is equal to, well, I don't know what it's equal to. Let's find out what it's equal to. It's equal to 0.057 times 0.99. And then we have to take the reciprocal of the number because I was just being lazy. 0.544. So what this means is that even with a 99% chance of testing positive and with a 5% chance of testing positive if you're not in the group, then you're actually only going to get about 54% of people given on this test. Yeah, so that's what it means. I should have just said, given that you have tested positively, right? That's really all I mean. And so here's the kind of dilemma that we run into with things like this, which we explained in a previous class, but I think it's always good to say it twice. The interesting thing about this is that what was I thinking about? Well, okay, so next we're going to run the test twice, but before we do that, I wanted to say something else, and now I forget what it is. Oh, yeah. So let's say that, if we tested everybody on the planet, right? And so there's about, what, like 7.2 billion people or something like that? Or how many people are there on the planet now? I don't know. I'll look it up. How many people on the planet? 7.594. So let's round that off to 7.6 billion. If we test 7.6 billion people, then then the question is like how many people are, if we test everybody, then the question is like how many of those people are going to test positive, and the answer is 10% of them, right? So it's going to be what, 10% of the world test positive, so approximately 760 million will test positive, but how many are the actual true results? And so we know that if we multiply the 7.6 billion times the 0.057, we actually get 433 million actually in group H. So what this means is that if you tested everybody in the world, you would expect that there would be about 760 million positives, of which, I mean, of course, it's actually rejecting. There's a few people who have it that are getting rejected, but we're actually only finding about 433 million of them. So we see that, like, even with these very high numbers, like 99% and 95%, 95% is a real problem here. That's the one that really kills you. If it's closer to 99%, then it would improve this a lot. If it was like, 0.999, then that's just great. So yeah, let's run the test twice now. 0.057, let me try to remember that number. .943 here. So either you test positive or you test negative. And then if you test positive, we'll test you again, so positive squared. This will actually be positive negative, right? And then here we'll have positive squared again, so you test positive twice, and then here we'll have positive negative. And so let's just keep the same numbers. So if you're positive, it'll be 99%, 99%, 0.01, 0.01, and here it'll be 0.05, 0.05, here it'll be 0.95, 0.95. And of course here we again have to assume that the error that's happening is not some kind of systemic error in the test. We're assuming that the two errors are kind of like flipping a coin or rolling a die, in the sense that they're kind of random errors that can occur in any test, right? So like a bad batch or something comes up positive when it's actually negative. Something that causes the test to be the wrong result, but isn't something that if you run the test 100 times, you're going to get the same result every time, because otherwise these two numbers would have to change. So now what we want to do is we want to compute the probability that you're in group H given that you're in group plus squared. So what you do is you calculate that, so it's equal to the probability of H, intersection plus squared, divided by, what is it? The probability of H intersection plus squared plus the probability of not H intersection plus squared. I like how many symbols we have now. These are good symbols. Okay. So this is equal to 0.057 times 0.99 times 0.99. And so in the denominator, what we're going to get is the same thing, 0.057 times 0.99 times 0.99 plus, and now we have to go down the not H path to the plus squared. So we want to go here now. So first we have to go here to the testing positive twice, and then we want to go here to testing positive twice. So we're going to say 0.943 to 0.05 to 0.05. And so now if we calculate this number, which we should do, let's calculate. 0.057 times 0.99 times 0.99. That's equal to 0.0558 something something something, who cares, plus plus 0.943 times 0.05 times 0.05. So now the denominator is something around there. Yeah, so basically, so we're looking for the probability of testing positive twice, because that's the thing in the second slot. And so the thing is, if you test positive twice, you either are in haplogroup H or you're not, right? So this is you are in haplogroup H, and this is that you're not in haplogroup H. And so this thing is equal to whatever it's equal to. Nope. So it increases to about, if you test the people again, yeah, it ends up being about 95%, I think. Which is, or I guess 96 if you're going to round it up. But whatever, somewhere between 95 and 96%, which is actually pretty good, right? Now you're much happier testing people. If you know that you're only going to get, say, about 1 in 20, that's a false result. Whereas if you tested people and you had something like a 50% chance of, half the people that you selected actually have this haplogroup, and half the people that you selected don't have the haplogroup but tested positive. So it's very helpful because you sorted out 90% of the population, but it's not as helpful because you can't be guaranteed that you're actually right or wrong anymore. Okay. So I wanted to talk about this one. This is definitely too hard for a test question, but I think, but if I walk through it, but it's doable in class, unlike the last one. So this one actually had me. I was thinking of putting it on your exam too, except for the fact that I had a hard time coming up with the right argument for it. So I was like, well, never mind. But I gave you the hint that I gave you a hint that the book that I got this from would not give. So here is some really crazy fun identity. N times n plus 1 times 2 to the n minus 2 is equal to whatever you get when you sum up k squared times n choose k's. So that is pretty nuts. And so I gave this little hint here. And the hint basically tells you how to think about it. So what you want to do is you want to think about it this way. So as it turns out, you can rewrite this thing, n times n plus 1 times 2 to the n minus 2. And you can rewrite this as n times n minus 1 over 2 times 2 to the n minus 1 plus n times 2 to the n minus 1, like this. And so I think you can do this because, yeah. So the point is that when you see this thing, what should you basically think of? And so I guess the way to think about this is, let's look at this summation for just a second. So let's look at this thing. So what is k squared times n choose k? And it's like, I don't know. But what you can do is you can think of it as, out of a bag of n things, pick k things. Right? That's n choose k. That's what n choose k means. And of course it's without order, right? No order. But then this k squared thing should bother you, right? This k squared thing is a little bit annoying because it's like, what do you do with this k squared thing? Well, here's what I'm going to say you can do with the k squared. Is basically you pick two elements out. So you pick out two elements. Out of this thing, and what you do is you star them. And so when I say you pick out two elements, there's also another thing that you can accidentally do, or you can pick out one element, and if you do that, then you have to star it twice. So let me just show you an example. So if I have all the numbers between, say, 1 to 10, and I want to pick a group of like 3 numbers, so then I pick out, it's not in order, I mean no order. So when I write down the symbol n choose k, what I mean by that is it's the number of ways to pick out of a bag of n things, pick k things, such that it doesn't matter how, or, it doesn't matter if order, it doesn't matter what order you pick those k things in. So for instance, if I pick 3, 5, and 7 out of the numbers here, or if I pick 7, 3, and 5, or if I pick 5, 7, 3, these are all considered the same combination, right, out of 10. Whereas they would be different permutations, but they're the same combination. When I say that the test will be on Blackboard for several days, does that mean it will be continuously available? I hope so, yes. So basically the way to think about this is that there's really two things that you can do. Either you pick two elements and you star them, or you pick one element and you star twice. And so there's another way to think about doing this. The other way to think about doing it is to pick two elements that get stars. And the number of ways to pick two elements is n choose 2, which happens to be n times n minus 1 divided by 2. And then what you do is you can pick any subset, any remaining subset, right? Because you see that k here goes from 1 up to n. So it doesn't matter as long as... So the size k changes from 1 to n, so there's all the different subsets. So the number of different subsets of n... The number of different subsets of n minus 1 elements is two to the n minus 1. So this is just pick some subgroup. Or we can pick star one element. So if you pick one element out, there's n choices, right? Because n is equal to n choose 1. And so there's n choices of ways to pick out one element. And if we do that, then what we're going to get is so we pick one element, we star that twice, and so that's n times the number of ways to pick out of a bag of n things, just to pick a group out of that. So this is the number of ways to pick out of a bag of n minus 1 things. I guess I've already run way out of space. So, but yeah, this is the number of ways to pick, come on, select. So, yeah, so this is the number of ways to select some group out of n minus 1 things. And this is the number of ways to pick a single element and put 2 stars over it. So basically, if for instance we had like 5 choose 3, it would be like what, 3 squared times 5 choose 3, which basically means like out of the numbers 1, 2, 3, 4, 5, we're going to pick the numbers 2, 3, 5, and then we have a bunch of different choices. Maybe 2 gets a star and 5 gets a star, or maybe 3 gets 2 stars, or maybe 2 gets a star and 3 gets a star. So those are all different possibilities for how to star everything. So this is kind of the combinatorial argument that shows that these two things are equal. Of course, you kind of have to rewrite it like this, because once you break it down like this and you say, okay, this is like n choose 2 times 2 to the n minus 1 plus n choose 1 times 2 to the n minus 1, then you kind of have it. Whereas if you do it some other way, then it's way more confusing. So yeah, so basically this is an interesting problem, and I saw it and I tried to solve it myself, and I had some trouble coming up with the argument for it, which it made me kind of interested more in it. So I just wanted to present it, but we might give a combinatorial argument on the final exam. I just wanted to make it something that it's going to be way simpler than this if I do. Because this one is horrible. Or not horrible, but it's just way too interesting and way too messy. Okay, so let's get back to more practice exam stuff. So let's do this kind of stuff. So yeah, well, I mean, it's not going to... So the rule in life, right, is if it took me a day or two to solve it, which it took me a day or two to figure out the trick to that problem, it is definitely not a 203 exam question. If it takes me somewhere on the order of like 5 minutes to solve, then that's reasonable for an exam question, you know? So if I already know, you know, if I don't have to think too hard about it because I know the trick or something, then it might be okay. Will there be an exam 2 answer key? The answer is I might write one tonight or tomorrow. Yeah. Okay, so is it the case that n log n is O of n cubed? So you have to remember what O means. So O means that f is less than or equal to a constant times g eventually. And so a simple way to argue that this is true is to basically say yes, because n log n divided by n cubed the limit as you go to infinity of n log n over n, so you can cancel out one of them and you get n squared in the bottom. And then you just have to remember that log n is really slow. So like the limit of log n over n goes to 0 as n goes to infinity. So that's one way to do it. Another way to do it is just to argue that the log of n is simply less than n. You don't have to actually say that it's asymptotically less than n. So if you know this fact, which I went over in class, I think, on the asymptotic analysis day, then you say that n times log n is less than n squared, but n squared is less than n cubed. So that's another way to say it. And of course, if you had to multiply things by some constants, then that would be a way to do it. So there's a number of different ways that you can kind of attack this problem, but your eventual goal is just to show that the first function is less than or equal to the second function eventually. So here's a fun one. Is 2 to the n in the set of big O of n factorial? So there are algorithms that actually run with factorial complexity. Mostly they're recursive algorithms that run that way. So some algorithms actually can run with a complexity of n factorial, which means that basically they're useless, right? An O of n factorial algorithm is generally kind of useless. You might be able to say, like, oh, it will eventually solve the problem if we have, like, you know, infinity seconds. So if I do a multiple choice type of thing, then I think I might give you guys, like, a few hours to solve the multiple choice section once you click on it, right? But you'll have any time to start. Or if I just release it in the standard way, then I would basically just give you continuous access the whole time. Okay, so is 2 to the n O of n squared, or I'm sorry, is 2 of n O of n factorial? And so here's the thing. Ooh, dog bark. Here's the cool argument that kind of gets you there. 2 times 2 times 2 times 2 dot dot dot. Okay. I really promised myself that I would clean up this office, but it's actually more of a disaster now than when I started teaching at home. The dog's downstairs probably barking at my neighbor because I have a door that she can see through, so she doesn't like it when people walk close to the house. So, okay, so here's a cool way to show that n factorial is bigger than 2 to the n. So how many terms are in this thingy? There are n terms, right? Because it starts at n, then n minus 1, n minus 2, n minus 3, all the way down to 5, 4, 3, 2, 1. And so what we get to do, so remember that big O always says eventually. So you're right that it's not true for low order terms. Well, so what I really mean by this is that big O is like a set of functions, right? It's the set of all functions such that they are less than c times n factorial, right? So you could say is 2 to the n. You can get rid of this in the in notation. I just kind of like it because I think it's is this in this group of functions. But anyway, we're getting past the trick, which is the best part. So So this is not true, right? It's not true that 2 is less than 1. So that's a slight issue. It's also not true that 2 is less than 2, so that's a slight issue. But it's true now that 2 is less than 3, 2 is less than 4, 2 is less than 5, all the way up to 2 is less than n, right? So we have all these terms that pair off, except for the first few of them. This one is equal, so whatever. And then this one, we can split this into 2 times 2, so we can kind of share the 2 over here, and we can keep a 2 here. So now this is no longer greater, it's just equal. And then this term is also equal now, since this is 2. So what we do here is, as long as n is bigger than, say, 4, right? And I think you might even be able to say bigger than or equal to 4. Yeah, as long as n is bigger than or equal to 4, this is true. And so if you remember the definition of big O, it says that for all, that there exists a constant n0 such that for all n bigger or equal to that n0, 2 to the n is going to be less than or equal to a constant times n factorial. And so in this case, actually, we can just pick that constant to be 1. Really, if we were even more lazy, we could pick that constant to be like 8 or something and then distribute the extra 2's. So as it turns out, the fact that this existence of this constant, why is it not n bigger than or equal to 3? Because 3 factorial is 6, and 2 to the 3 is 8. So it's not quite bigger yet, right? And the reason for that is because, remember what we had to do? We had to take the 4 and split it up into 2 times 2. So we had to take this 2 and push it over there. So as it turns out, 2 times 2 times 2 is still bigger than 1 times 2 times 3. But again, you know, all of this low order stuff, like Big O doesn't care about it eventually, because we really care about what happens when n gets large. So say n is on the order of a few 100,000 or million or billion or something like that. So anyway, yeah, so this is like, I think this is a fun one because you get to basically draw them out and say, well, 2 to the n means this, n factorial means this, and then you get to pair off the terms one by one, and just, except for these bottom ones where you have to do this little bit of trickery, it's true that the less than signs apply for all the stuff inside of this ellipsis, right? These are all just 2's inside of here. And inside of here, it's like 6, 7, 8, 9, all the way up to n minus 1, right? And then up to n. So it's always true that 2 is less than whatever this number is in here. And so eventually the n factorial is going to grow pretty big. All right, so here's a false one. So is n factorial big O of n? And so let's try to show that it's not. So what we do is let's assume it is. And so what we know about that is that therefore there exists some constant c and some constant n0, so that if n is bigger than or equal to n0, n squared is less than or equal to a constant times n, right? So for any sufficiently large n squared is less than or equal to a constant times n. So that's, this is what we're assuming. And then the problem here is, what you can do is you can just divide by n each time. So you get this. The number n is less than or equal to the constant c. But then you would say, wait a second, I can always pick n as long as it's bigger than or equal to n0. So as long as basically you can just pick it to be something way bigger than c and n0. So pick n to be, say, the max of n0 and c plus 1, right? And so if, what we really want to do is we want to say that c plus 1 is less than or equal to c. And if we say this, then we say, wait a second, that can't be right, because if you cancel out the c's, then we get 1 is less than or equal to 0, which is false. So if that's false, then what we know is that this had to be false. Therefore, this had to be false. Therefore, this had to be false. Therefore, the only thing we assumed was that, so you ask, is n squared big O of n? And the only thing we actually assume is that it is. So actually, what we would do is we draw a little contradiction symbol, and we say, oops, it isn't. And of course right, and so that's how this type of proof ends. The proof ends, I mean, this is what I usually draw for contradiction. I've seen this. This is like a pretty common contradiction symbol. But you can always just say contradiction. And then the only thing about a proof by contradiction is that you have to remember that, like, essentially we are proving that there is something false in our argument. So either it's false that 1 is less than or equal to 0, or and if that's false, then this is probably false, and this is probably false, and this is probably false, right? And these things are all related by the rules of algebra, which we're not going to assume are the thing that's causing the contradiction. We're going to assume that algebra works, right? We're also going to assume that this statement here is correct, because that's the definition of big O, right? So you can't really contradict that, because it's just the definition. If the definition is contradictory, then don't worry about it. So the only thing we actually assumed was the contrary of the thing that we were trying to... the thing we were trying... Yeah, the contrary of the thing we were trying to prove, because we were trying to prove that it isn't. I don't know how to do that, so assume it is, and then you show that something like 1 is less than 0. So I'm going to release this because I have run out of time, as you can see. This is one problem that I might want to do a little video. Maybe tomorrow I'll do a video on it. I wrote this problem down, and I think that it's kind of interesting. So, yeah, and I'll show you what I want for it. It's a good problem for multiple choice, actually. And then here's an extra credit problem that I won't go over. I don't know, maybe I'll do it live, or I don't know what I'll do. I'm also going to give a review session for 201 tomorrow, because I fell a little bit behind this weekend, and I needed more time to prepare for that. But anyway, I guess I'll see everybody tomorrow. All right, I'll send this out to you as something. Maybe I'll post it on. Let us download this board. And I've been saving them to the desktop, and then I'm going to export. I'll send them out in an announcement so that you guys have access to some of these. All right, well, cool. Nice review session, huh? So when will the exam be released and when will it be due? I was thinking of probably releasing it sometime, maybe Wednesday, and then having it due the following Wednesday, something like that. Giving you guys a full week. Yep. All right. I guess that's it. If you guys, I'll keep the Discord open. So, you know, if you guys want to, if we're still locked down and you feel bored, You know, you can always bother people on the Discord even after the class ends. I'll try to be responsive there. Other than that, have a good summer break. Try not to go crazy. All right, and I'll send out the final exam, and we can work on it. All right. Thanks, everybody. Hopefully. Oh yeah, and fill out the course review. Fill out the course review. Because I've only gotten like 17% response. So, all right. And I'll see you guys next semester, hopefully in person. All right, bye.